Hey, what's going on, guys? Makikins here. In this video we're gonna be applying so-called late move reduction to our search to improve it even more and to reduce the number of traverse nodes significantly. So before we start, I'd like to tell you a little story on how I came up with the idea of late move reduction. Well, obviously I heard that late move reduction is actually available, but the point is not just to blindly pick up some fancy techniques and trying to embed them into your research, but trying to follow some sort of an inner flow, leading your mind to the ideas like where exactly we can save the performance, well, not save the performance, where exactly we can save some nodes within our research. So the idea that I came up with, I did ask a question on talkchess.com, and here is the exact thread for that. And the idea how I wanted to implement this was really weird, and I got heavily criticized by the community for this idea, for being such a noob and asking such a noob questions. But that's not the point. The good thing is that eventually I got a reasonable help from the guy here. Just give him a credit just right in a moment. Who actually pointed to the implementation of late move reduction, how it should be done basically, and that's the exact implementation that we're supposed to be using today in this video. And as far as I don't really have that great understanding of the implementation in particular, I would rather just go for all those steps I've already done before to show you like how I was approaching, and then we'll have like how it's working. So anyway, my initial idea was to assuming that we have a move list, right, and assuming that most likely some of these moves that are scored like either like PV move or captures or some history moves, if any more, then that's great. So that most likely the cutoff would be produced by one of these moves, which is a well-known assumption. I didn't invent that assumption. And what I was trying to do is actually to not search those moves that are scored as zeros, assuming that they don't make any sense at all. And when I tried to do this, I got almost doubled improvement on reducing the nodes, but when I tried to test this to play versus TSCP, it was like blunder in pieces and got mated every time, because not searching this move is really bad idea, so you really shouldn't do that. But the initial intent was actually trying somehow to save save the nodes on traversing these moves that are not ordered that great. And here is the entry point where the late move reduction comes onto the game. So here a guy called Pearson, I'm sorry if I'm pronouncing his name wrong, so he would look into and implement LMR, late move reduction, and so on. So I asked him to point out the LMR implementation, and here he points me to this sort of an implementation. I'm not sure who is the author here. I'm just wondering who is the author. Was popularized by, so I'm not sure whether the author of this is Tord Romstad, the author of Stockfish. I'm not really sure, but for some reason I was thinking that he is actually the author. Okay, hold on a sec, guys. I just need to figure this out quickly. Okay, so assuming this domain name, let's say, even though it's an archive, it's not already available on the internet. Probably that's the reason for storing it here. So glaurung is the chess engine that was written by Tord Romstad for sure, and by the way, Stockfish is the successor of the glaurung chess engines. So that's the reason why I assume that this article is actually written by Tord Romstad. While I'm not can be 100% sure, still it seems like it is about to be so. So I will leave the link in the description below this video pointing out to this sort of a resource. And before we start, here we have a very fantastic, I would even like to say, the didactic implementation of the late move reduction. So the main idea is that instead of actually not looking to those moves scored as zeros, like I was initially trying to do, but instead trying to reduce the search depth for those nodes. And just like we did with the principal variation search, if that idea fails, so if one of those moves searched with a reduced depth would actually show itself to be a good move, then we will research it again from scratch with a full bandwidth of the search scores like alpha and beta. Okay guys, so I hope the idea is quite pretty clear, but when it comes to the particular implementation, it's not really exactly that I've just described, because it's not really the matter of taking into account the score of moves, but instead what Tord's, well, I assume that this is the article by Tord Romstad, so I would have seen, like, I suppose what Tord suggests to do. So what he suggests to do is actually to make sure that the search move is greater than, sorry guys, that full depth moves, and it's equal to 4. So he wants to make sure that the first 4 moves has been searched at the full depth, and usually the first 4 moves are like, first is the principal variation if available, and then the captures, and then so on. So that's the idea. And another condition, so depth should be greater or equals the reduction limit, so at least the depth of 3. Well, this reduction limit parameter can be changed, and you can play around with this on your own, but I really like the current reduction limit of 3. It works like a charm. And then this OK to reduce, this is quite pretty sophisticated topic. So there is a stuff called search instability that maybe I will learn in 10 years what is that and how to deal with that, and also things like search extensions, which is also too complicated to me. So what I just want to say that I've just dropped this condition, and I just used this conditions, and that's it. And instead of this OK to reduce, I used the only parameter, like I didn't reduce the depth only in case if the king was in check. So there is a list of parameters to when we want to avoid reducing this sort of a depth, and one of the main is actually to not reduce the moves if the king is in check. So instead we want to increase the depth, and we're doing that in our research actually. Okay, yeah, so without further ado, I would actually now start implementing the late move reduction, and basing on this sort of a code, and we'll try to test how it works, and then we'll go. So another little thing to consider, I just wanted to add one more little schema. Where's the move scoring? Here. Score moves. Okay. Yeah, so here before we score in the moves, I just wanted to add this little schema pointing out the move ordering, like how in particular we order our moves. So first it goes like principal variation moves, then captures in MVVLV, second killer, history moves, and sorted, and so on. So I needed to do this a couple of videos ago, just forgot to do this, sorry for that. Okay, and now we need to go to our Nigamax search definition, and here we go. So the first thing, we just need to define this to variables, so full depth moves and reduction limit. So I just renamed the variables in the style I used to follow in this source code. Full depth moves. Okay. Full depth moves like this. Okay, let's try to compile and run this to make sure it's error-free. So make debug, and if it makes, I want to run the BBC binary executable. Okay, we'll now see the number of nodes we have after applying principal variations search, so 800 thousandths. Okay, and slightly more. Okay, so move search. Okay, so move searched to be defined at the very top. Okay. Okay, move search. So let's define this then here, just right below. So moves searched. Let's say number of moves searched in a move list. So we're searching moves in a move list, like kind of one by one, and this variable stores the value of moves that has been searched already. And by the way, I'm just wondering, I don't really remember how I did this before. So I can probably define this even here. Okay, just hold on a sec, guys. Yeah, actually, I did it like that. So let's do it like I already did. So here, so this, it seems to be, is this the loop? Over the move list. Okay guys, just hold on a second. I want to reference my code that I've already tested. So yeah, just right before this. Okay, so before the loop over the moves. So let's put it here. Move searched equals to 0. Save. Okay, and what else? And the place where we increment this. Okay, so and make move and move searched plus plus. I'm just wondering where does he have the beta cutoff, or this is the trick to avoid that, probably. Well, so probably, so at the very last, yeah, so after we're taken back and do all the scoring stuff, but at the same time, okay, just again, I'm sorry guys, I just really want to reference my code to make sure it's gonna be working. So yeah, I did this right after take back. So if beta cutoff occurs, okay, so let's do this the same here. So as far as we take back, here we just want to increment our moves searched. Increment the number, the counter of moves searched so far. Okay, so this is it, and here is the logic. So we use this move searched, right? And okay, so yeah, starting from here. Okay, yeah, just grab this entire code. Okay, by the way, from the previous part, I just want to delete this principal variation search related commented code. Okay, and so we want to be working here. So if principal variation search actually is not on the cards, in this case we would be working right over in here. So I just want to paste the entire code so that, okay, use it while embedding it into our engine. So if moves searched, so if there are no searched moves, okay, so if there are no searched moves, in this case we want to do our normal alpha beta search. So this is the very first condition. So I can say if moves searched equals to 0, in this case we just do our normal search, okay, and otherwise goes this late move reduction stuff. So yeah, let's try the condition. Copy. So I just call this condition to consider late LMR or late move reduction. So here I say like no moves. So let's say full depth search. Okay, and here we go for our late move reduction. So late move reduction. Okay. Or even better like this. So late move reduction, so condition to consider late move reduction. So instead of this okay to reduce, I say not in check. So in check is equal to 0. Okay. And let's bring it here. Okay, and now just want to adjust the variable name, so full depth moves and the reduction limit as well. Okay. Okay. So yeah, this seems to be correct. So search move with a reduced depth. Yeah, this is exactly what we want to do. Okay, so let's grab this part. So yeah, nothing to add here, but just search this move with, let's say, current move with the reduced depth, and this minus alpha plus 1 is literally the same that we did here, minus alpha minus 1. So just in order to avoid confusion, like maybe there's a different values, so I just want to use the exact definitions here. So these expressions are equal from the math perspective. Okay, and we're reducing the depth, so depth minus 2 instead of depth minus 1. So doing two things, reducing the depth and also reducing this, well, doing something similar to what we've been doing to principal variation within principal variation search, so narrowing the bandwidth of the scores within the alpha beta, something like that. Okay, and okay, just hold on a sec. If move searched, oh, I just did put this else into wrong position, sorry. So I don't actually even need this. Yeah, I don't need this. Curly braces. I'm not exactly sure what does this line mean. I just leave it for the further generations, much smarter than I am. So maybe somebody would ever explain me what does this hack to ensure that full depth search is kind of re-enabled. Well, probably if we did this -1, did to subtract -1 from alpha, now we just subtracting it, now we are adding it back. I'm not sure. Hold on a sec, this is done is misplaced, so to hack, that hack is done. Okay, so paste. Okay, so otherwise we're restoring the value of alpha, and now we need to do something similar to this check. So if the idea of late move reduction actually fails, so we find if during this late move reduction we'll find the moves that were seemingly bad, but it turns out that they are actually good. In this case, we need to search them again with a normal depth. So that's the idea of the following code. So let's have a look. So if so if reducing, go in this line, otherwise we're restoring alpha. And okay, so he uses value, which in my case this is the score. Okay, this is the score. And in the case if, yeah, this is it, yeah, just got this. So in the case if value or score, so let me just change the score. So if case is score is greater than alpha, so this means that we actually found like kind of Prince PV node according to Bruce Moreland's terminology. So if it happens that we actually do find a better move within those moves ordered in the bottom of the list, but suddenly it appears that some moves are reasonable, really. So let's say if found a better move during LMR, let's keep it abstract like this. So in this case, or hold on a sec, what did I just say? So he's actually doing this the same, or hold on a second, just, well, I can definitely replace this expression, but no, actually the check whether it works or not is happening here, so it's exactly the same like we've been doing here. It's the same line of code. To make it match even more, just add a couple of parentheses. Let's say if MLR fails, research at full depth and full score bandwidth. Okay, I'm just wondering. Oh, probably if it just finds a better move during the late move reduction, so if score is greater than alpha. In this case, okay. Oh, this is interesting. Whoa, this is really interesting. So I like this like moments when I suddenly started to understand something. Okay, guys, so here is the point. So here we did search with the depth -2, but if we find a better move during the late move reduction, we keep our score bandwidth, just like we did in principal variation search here. But already we trying to search like, I'm not sure, but it seems like it's researching this again. They found a better move. Research at normal depth. Okay. Yeah, it seems like. If I'm wrong here, please correct me, guys. Okay. Well, actually, research at normal depth, but with narrowed. Well, they call this aspiration window. This bandwidth between alpha and beta window. Or maybe I'm not allowed to use this term here, I'm not sure. Well, let's to make it 100% sure, let's actually call it like this. So scored narrowed with narrowed score bandwidth, and if it fails, in this case research at full depth, well, at normal, let's say at full depth, but with a narrowed, and here we research with at full depth, but with a full score bandwidth. Yeah, so we restore the minus beta minus alpha here. Well, okay, guys. So at least this seems to be like it's correct. I'm not really that sure. So now I hold my breath and we'll try to actually test this. I hope the search is not gonna be 3 times slower after my modifications. Okay. I really hope so. So our current number of nodes is this one. And holding my breath and try to run this again. Okay, what's wrong? Oh, not minus search, but minus nigamax, obviously. Copy minus nigamax minus nigamax. Yeah, it's time to pray. It's really time to pray now. So what it would make. Oh man, don't tell me it's greater than we had. Oh man, this is greater than we had. Same story again. Which means that I missed something, did something wrong. Okay guys, just hold on a second. I need to figure out what was wrong here. Okay guys, so one of the differences I've already found is actually in my original code. I was also checking whether this this OK to reduce also involves checking whether the move is not a capture or not a promoted piece. So well, let me actually show you this in the chess program in Wikipedia. Let me just find the LMR article here. So, okay. Late move reduction. Just to give you an idea of where I taken that. And I know, like, guys implementing really so complicated and sophisticated functions to actually make sure that it's okay or it's not okay to reduce reduce the depth. Okay, late move reductions. Okay, this is it. So here we have the common conditions. So well, this depth is less than 3. Okay, tactical moves. Okay, tactical moves, captures and promotion. So do not reduce this type of move. So it's a capture or promotion and in check. So I've used this too out of this. Well, I'm not sure regarding this depth is equal less than 3. It's probably the same as. This is probably the same as depth is greater or equal than reduction limit. I guess this is it. At least assuming the reduction limit is 3, it seems like to be. So. Okay, so anyway, Anyway, I just want to change the layout slightly a bit. So in check is equal to 0, okay. And here I also want to make sure that move is not a capture, so get move capture would be equal to 0, so it's not a capture, and here the move itself. Okay, move list, moves, and count, I guess this is it, right? And also the same for the promoted pieces, so get move promoted. It also shouldn't be the promoted piece, so this is what I have here. And if this doesn't work, I don't even know what to do else, so okay, let me just get rid of this course. Okay, so this was the previous unsuccessful attempt. Also, by the way, so we don't want to reduce the depth for principal variation nodes and principal variation search, and that's the reason why I'm doing all this late move reduction stuff outside from here. So if we fall into the principal variation node, in this case we do its own stuff, but otherwise we actually attempting to make this late move reduction. So actually I'm using conditions like 1, 2, probably this one, probably this one. I don't check for the condition when move is given a check, because I don't know how to do that at the moment, and I'm not dealing with the search extensions, which is a really great topic on itself. It's really sophisticated for me at the moment. Okay, so bearing in mind that not reducing the captures and the promotions, it now should hopefully bring some improvements to our search. Okay, oh my god, did it become even worse than it was? Oh no, it's even worse now. This is bad. Okay guys, so I will now continue my research and get back to you. Okay, hold on a sec, I've just realized that I didn't save the code. Still, it's not clear why it was more nodes there. Okay, so if I just try to comment this stuff out completely, I just want to get the initial number of nodes. This one. 856,924. Yeah, this is it. Okay. Okay. Yeah, and now I will go for my research. Okay guys, and another downside of copy pasting is that obviously the condition for failure of this late move reduction should be done within this if score is greater than alpha, which I didn't. I did this separately. So okay, and I'm gonna watch the dramatic reduce of nodes in this video. Oh my god, hold on a sec. hold on a sec. So what, it was already here. Okay. Whoa. Well, don't tell me it's gonna change. It should be this weird big number, this one. Yeah. Okay guys, so sorry, I was okay. Well, okay guys, so quite a fun thing that actually this late move reduction implementation seems to be correct, and that just was the matter of position. So when I changed the position back to tricky position, the expected the expected behavior was actually reached. So I just want to demonstrate you this now. So I didn't literally change anything. So let me just again like kind of show you how it's supposed to be working with without this late move reduction, but already in the tricky position, having this lots of captures. In this position we've been searching. So it has this 824253. Okay, so lots of captures. And if we just now enable our late move reduction in this position, and yeah, just like I was already mentioning, it's so let me just copy. This is the position I was initially testing when implementing this late move reduction. But in composition it seems to be getting, well, this is quite pretty expected. Oh my god guys, it seems like I just understand why this is happening. Okay. So like in this position we have, can you believe this? It's even slightly more than twice less number of nodes. So this is the result. This is that significant result I wanted to show you guys. So you know, like this is a real insight for me personally, that it gives actually even more nodes in compositions, but it goes so nicely when it comes to tactical complications. Okay, so let me just share my theory on why this is actually happening, and please correct me if I'm wrong basically. So my idea, my assumption is that, assuming that we're doing our late move reduction, so when we're doing our late move reduction, we really hope that the moves that we're reducing depth for would never produce the beta cutoffs. So they're not good enough. That's the reason why we're reducing their depth. And the probability of those moves to be actually to fail that condition of being bad, so is very low. So it's most likely they're reduced, and that's just okay. Don't no worries regarding that. But when it comes to the composition, it's normal that the moves that are scored lower compared to the first captures even and things like that, they can be actually be a better move. They might not be that bad at all. And in that case, we would be researching this again. So gotta making a double job here. If it turns out that we found that there is a better, that the move that we will find a better move where we're not supposed to be finding that. Yeah, so that's my theory basically, and this is the reason why it reduces the number of nodes so dramatically in tactical position involving lots of captures, and why it goes a bit slower in compositions. Yeah, this is really interesting. So it kind of forces engine to more like trying to go for aggressive tactical lines because it's calculated much faster there, and it would take him kind of a bit longer to deal with the compositional moves. And yeah, that, by the way, this opens the highway to playing like versus chess engines as humans when we want to reach a compositional position, just to do some maneuvering without tactical lines and captures. And that's why humans can outplay engines sometimes when engines are not really that strong. So, well, this is really interesting insight for me, to be honest, guys. Until this exact moment, I didn't know that this is actually kind of possible. I didn't think that the behavior with the non-tactical positions would be so different. I really didn't know this. So it's quite pretty interesting and good insight to consider, obviously. So yeah, this is very interesting. Okay, guys. So I hope you learned something interesting out of this video along with me, and I just feel a bit confused by the results that I've just realized. But anyway, the implementation by Tord Romstad has just been embedded into our chess engine, and hopefully would make it playing better chess and working faster. Well, at least in this tactical positions. So that's kind of it. And now we can even go to the depth of 7. So just increasing the depth. And let's have a look. I'm just wondering how many nodes we'll have at the depth of 7. $1 million. So it's almost equal to the number of nodes when we had at the depth of 6, when there was no principal variation search, and also when there was no late move reduction. So it's like it gave us for about 1 ply deeper now, which is not really that bad at all. Well, okay. It's not the same for the compositions, obviously, but nevertheless. Well, okay, guys, yeah, I really need to think about this on my own because it's really so exciting. I've never ever been thinking that it works this sort of all the way. Okay, so chess programming is bringing lots of surprise into your life, I believe. Okay, so in the next video we're gonna be implementing a technique called null move pruning, and this is quite pretty simple technique, and even noob like Komakikin understands how that works. Well, it is. I think I do understand that. I'm not sure if that is really true after this insights. And I'm gonna be implementing the most simplified version of null move pruning available. So trying to make it as simple as possible, and that would already be the state of the engine that I've been demonstrated a few videos ago, like playing at depth of playing at 9 plies depth in the Arena GUI that I was showing you guys. Okay, so yeah, let's just stop this video here, and I really hope to see you in the next following parts within this Bitboard chess engine.